Go.
So our group did counting problems, and you want to read the first problem?
Okay, the first problem is suppose you have n pairs of parentheses.
Oh, a little louder.
Yeah,
Wait,
yeah,
I want
I
to
can't
get
hear.
slower. Suppose you have n pairs of
Counting.
suppose you have n pairs of parentheses and you would like to form valid groupings of them, where valid means that each open parentheses has a matching closed parentheses. For example, well, I'm going to
Here, I'll do that right there.
is valid, but is not.
Wait, can you move aside?
Step aside so people can see.
How many?
Roshan, you're blocking.
Okay. I'll be right here.
That's
So, David, you're walking. This is invalid because you see it has
How-
opening parentheses. Yes.
How many groupings are there for each value of n? Perhaps a more precise definition of the problem would be this. A string of parentheses is valid if there are an equal number of open and closed parentheses. If you begin at the left, as you move to the right, you add 1 each time you pass an open, and subtract 1 each time you pass a closed parentheses. Then the string is always non-negative.
Excellent.
Okay, so we're going to show you a little method that didn't work, but it's still important because we'll get to that later. So what we tried to do is we first looked at the open parentheses and replaced them with letter A, and closed parentheses replaced with letter B. So what we first realized is that any sequence of valid parentheses must start with an opening and end with a closing. You can't have that, or
We can have that.
you can't have that. You can't have that, or that, or that. Those are all.
When you write on the board, you got to step away so people can see. Otherwise, you're the only people who see what you write.
So this is the only one that's valid. So what we did, if we say, let's try 3 pairs of parentheses. So we lock the first pair, one there and there. So then you have these 4 more spots.
Next, 2 pairs of parentheses.
2 pairs of parentheses where you have 2 A's and 2 B's. So what we tried to do is we tried to look at how many words we can form using 2 letters A, and B, B. So that's 4 factorial divided by 2 factorial times 2 factorial. 6.
Oh, we have a problem.
Right, because there were invalids in that.
Step aside, move with people and see people always. Does that make sense to you guys?
Yep. Yes.
I am inside. You want me to step aside more? Okay, there was an invalid. It was this right here. That's invalid.
And this is where we realize that it's always invalid if you have an A, and then if it's balanced out somewhere, you have some number of A's, and then you have more B's than that.
So
where that's
I don't know what he's talking about, but anyway,
Then
yes.
that's right.
So I have a question. Is something automatically not valid if you start with a B?
Yeah.
Yeah, because this is a, but we lock the first A and B, so really we're just looking at the inside.
Yeah.
But the inside can start with B.
The inside can start with A. So anyway, so that was 1 invalid. 5. So with 3 pairs of parentheses, it was 5. No. Okay, so anyway, 3 parentheses is 5. And then with 4 parentheses, what we did was we did the same thing. So you have locked the first outer pair of 1, 2, 3, 4, 5, 6.
Wait. I have a question for that. How do you know there's no other invalid situations for 3?
Well,
It's obviously.
this is what we're, well, in n equals 3, there's so few cases that you can just run through all of them.
Okay.
David, out.
I'm not going to take it. So anyway, in n equals 4, you have 3 A's, 3 B's. What? So then number of words you can form is that, right?
Yeah, minus invalid.
That's 6 just 3.
Oh.
Yes.
3. Okay. Anyway, it keeps going on like that. But the problem is, as we got into higher pairs, more pairs, the number of invalids, we couldn't keep track of them. There was no pattern we could perceive.
Because we had stuff like A, B, B.
And then
That obviously doesn't
we
work.
had a method for finding invalids that didn't work at all
No,
because
no,
we
no.
left out entire cases.
Okay, so once we got stuck on that for a little while, we tried something else. We went back to what the problem said about the number line thing, where every time you have an open parenthesis that's plus 1, and every time you have a closed parenthesis that's minus 1, and you're walking along the number line, and you can never go behind the 0. So, you were working on something, and then I figured out what
It was Isaac and I. We were working on
Guys,
saying.
very important person who speaks is at the board and the other to stay on the side, flat to the wall.
So Isaac and I realized that this will help. Isaac and I realized that what we could do is say that we have 3 pairs, so n equals 3. Okay. So if you have 3 pairs of parentheses, at most you can have 3 opening parentheses in the beginning. So you can go to 3 at the farthest, right? And then if you go to 3, then you'll automatically have to go back in 3 steps. So there's one way to go to 3. Then to get to 2, there was you could go if you go to 2, we already counted going to 3, so we can't go forwards to 3. So to get to, so you have to either get to 2 in 2 steps or 4 steps. So here we have 2 steps, and so probably just for clarity, I'm going to erase the old one. So you can get to 2 in 2 steps or 4 steps. This is showing 2 steps. Then you have to get back in 4 steps. So you can go here, go back here, go here again, and go back here. So that's 4 steps. And then to get back in to get here in 4 steps, we realized you
That's
could
6
go.
steps. But we just showed 6 steps, isn't it?
See, you go there in 2 and come back in 4, but going back, you go one
okay,
step in
going
this
back.
direction, so you have 3 in this direction. So we wanted to see how to get to 2 in 4 steps also. So we went to 1, back, we went back to 1, we went to 2. But there's another way that we had already counted. Because we could have counted going here, here, back, and here again. But we realized that since you had already been to 2, then it was like going to 3 in 3 steps and coming back. But we can't count it as going to 2 if we're going past 2.
Wait, what?
So here,
Yeah.
if we're getting to 2 in 4 steps, we couldn't have already reached 2 before and come back.
Oh, I get it.
So we came here in 2 steps, and then we just went back. That was the only way. So then there were
You're
there's
missing.
1, 2,
You're missing a case.
3 ways.
Wait,
There were 3. You only
There were
said
3.
two.
So there were 3 ways to get there. There are 3 ways to get there when 2 was the farthest you went. When 1 was the farthest you went, you could only go between 0 and 1. So there was obviously only 1 way. And 0, well, we could guess that there was no way where the farthest one you went was 0.
Okay, so can I show my pointer?
Yeah.
Wait, so what are you gonna do with it?
So we just added these and that got 5.
Yes, but
it
the
got
problem,
increasingly
Yeah,
difficult.
it tried to go farther and we got worse.
the problem with all our methods is that the more parentheses you add, the harder it tends to get to count. And that's when I came up with the flowchart.
Oh.
So let's go back to n equals. Actually, let's try n equals. Let's make them good. So 0, 1, 2, 3. Farthest you can go is 4. Okay? So we know that the first one from 0 must go to 1. And we know the last one from 1 must go back to 0. Right? So really, instead of 8 jumps, we can just assign our 6 jumps, starting at 1, making our 6 jumps, and coming back to 1, which last jump goes back to 0. So what I did is if you're at 1, how many choices do you have? Well, you can either go to 0 or you can go to 2. So 2 choices. Once you're at 0, you only have 1 choice. You can only go back to 1. One choice. 2, your 2 choices. 1 and 3. Now you're at 1 again. You also have 2 choices. 3, you're 2 choices. If you go back to 0, that's 1 choice. Go back to 2, still have 2 choices. But when you're at 4, you only have 1 choice because you can't go any farther. Now here, back to 1, still 2. Now when you get to this 3, you came to this 3 because you were at the 4. But because you're at the 4, you run out of plus 1s. So you must go back to 2. That's 1. Now that you're at 2, you must go back to 1. 1, and now you're back at 1. So that's like the end.
So there's a. It's still kind of a 1 because you're out.
Well, you're at 1 and you go back to 0.
You have to at 6.
Well, you after we set these, you can't.
Wait, is there any reason why you're like putting the numbers in like different rows and stuff?
Yeah.
It's like a graph. This is time.
Oh, it's the timing.
This is time.
There's no speed.
There's no speed. So that's time. So first time, at the first step, you have 2 choices.
Yeah.
The next step, if you're at 0, you only have 1. If you're at 2, you have 2 choices. It keeps going down.
Oh.
So if you're at
I
3,
will.
if you're at 3 after 1, 2, 3, 4, 5 steps, you only have 1 choice.
Okay. Yeah.
You
Okay.
can't be at 3 after 4. So what I did is now that we have these choices, we can begin to do this. Okay, 2 choices going out both ways. Right? So that's what it looks like. If you follow any one of these paths, that correlates to setting down parentheses.
Hey, that's cool.
So this is just Pathfinder 12. I thought this shape was just extremely complicated. I do it in a nicer form.
Hold on, right? You keep trying to.
Wait, what are you?
It's Pathfinder. You start 1 way here. 1.
Oh, yeah.
5. That's 5. 14. So with 4 pairs of parentheses, by following all these paths, there's 14 ways to start 1, get back to 1. And so basically, once you set up your beginning and your end, there's 14 ways to fill in that so that it's valid.
That is cool.
And
Now Roshan didn't like this because it was full of arrows and parallelograms.
if you start like not draw a straight line, that's mostly true.
No, I'm not across them. Okay. So what we did is that we kind of smushed this and rotated it a little bit.
Oh, and are you making it into one of those diamond things that you normally do into Pascal's triangle? That made no sense, but yeah.
I'll let them talk.
No, we don't. There's only 3. So after kind of making these parallelograms, pressing them so they're more square-like.
So instead of having diamonds, we just make them squares.
So every time you go down this way, that's equivalent to going to the right. Every time you go down this way,
If
that's
you turn
equivalent to
your
going
head,
down.
you see the squares.
Yeah.
Yeah. If you turn your head, you see the
Now Roshan didn't like his head turning to look like that.
Let them talk.
So now we can do this again.
Is that a 1?
That's pretty.
That is pretty.
So
And if you remember, 5 just happens to be the number of ways you can get there when n equals 3.
N equals 2 is 2, N equals 1.
No, Roshan, I think it's
Wait, watch it
it's the one
change.
above it that it should that you.
No, the 2, 2, 5, 5. They're just exactly the same. Just goes up.
Just mean drop down. We
Wait,
add
watch
it.
now.
Wait, how do you? What's your method for adding it?
I see it.
Okay, so you're starting from here, and you're getting to this
Guys,
corner.
you are closing the board and we are writing small, so you got to follow.
I
Alright,
can-
step
I can
aside,
see it.
take a yardstick, point from afar. Roshan, do you realize that behind you are sitting people?
Yes, I know.
Okay, so it's like one of those problems where you start in the
Yeah.
top left corner and you try to get to the bottom corner.
Yeah.
You can only go down to the right.
Yeah.
So you have one way to get to the first point. You have one way to get to this point from there.
Yeah.
One way to get to this point from there. And two ways to get this point from up here or from over here. And you just apply that to all.
So there's like a 0 down there between the 2 and the 1, and a 0 between the 2.
Yeah.
So that's n equals 4. But we realize that if we do that again and extend the number line, n equals 5, it's like this.
That's so cool.
5, 28, 42.
Oh.
Roshan, we have the computer.
And we looked at all these numbers and we checked it with Wittgenstein and she said they were all right, so they must have been right. So now we had a recursive formula.
Well, it wasn't a
Roshan.
formula yet.
Well, it wasn't really a formula, but it was. But it was a picture. We could keep drawing the picture as long as we wanted, and we will always get. We will always yield the number we wanted.
Yeah.
Now, before we generalize this, we went on to the other problems, which Isaac can explain to you right now.
Alright, so the second problem is how many mountain ranges can you form with n upstrokes and n
Here, you
downstrokes?
want to read the stuff behind Isaac on the board and draw what Isaac is saying?
How many mountain ranges can you form with n upstrokes and n downstrokes that all stay above the original line? If, as in the case above, we consider there to be a single mountain range of 0 strokes.
So basically, we go up, or once we go up, we can either go up or we can go down. We can go up or up and down. Basically, going up and down.
This is plus 1 minus 1.
Yes, but if we take the number line, apply it here again. We realize we're just going up 1, down 1. We're going plus 1 minus 1,
Yeah.
which we said already relates to parentheses, which relates to this design. So this design also be used for calculating mountain ranges.
Okay, problem 3. In a grid of n by n squares, how many storage paths are there that lead from the upper left corner to the lower right corner that do not touch the diagonal of the square from the upper left to lower right? In other words, how many paths stay up
You guys
on
want
or
to draw the
above
square and show an example?
Okay.
Don't, and blue marker is better. They find a good blue marker. So the people get to see. And step aside and let people see what you draw here.
Okay, question.
N equals.
See, Roshan, while you're standing there, erase all unnecessary things on the board
Okay.
and organize the space.
So basically, we're n equals 4.
Just erase that.
And
You
at
have
this
to
point of
take out-
time there, you want to step aside completely. Draw the diagonal you care about and explain one more time what you're trying to do.
This diagonal right here. Right? We have to, or this diagonal square, kind of. We erase that, take away all that, count it out.
Now step aside, both of you, Isaac and David. Take a pointer, look at people sitting far away, and Dennis and Anthony, and make sure you can make eye contact and they can see what you're saying.
So if we take out this, we will take out everything below that, then you get this staircase design again, which we already said goes back to that design, which relates to these mountain ranges and the parentheses.
Wait, but isn't it just a 3? Oh wait, no. Isn't
Well,
it
that's
just?
the corners of the 3 by 3. Aren't you touching the diagonal?
Yeah, or at the corners of the 3 by 3.
Oh, I get it.
Yeah, but look, this
It's
is
the
the
same
same as this too. Your style is the same as this.
right.
So on that, so we can only go along that.
Right.
We just kind of fold this in a little bit. It's the same number, so it doesn't matter.
Problem 4. Suppose two candidates for an election, A and B.
What?
Candidates for an election.
A and B each receive n votes. The votes are drawn out of the voting urn, one after another. In how many ways can the votes be drawn such that candidate A is never behind candidate B?
Well, you want to explain it?
Okay, well, this is just +1 -1 because you're drawing them out one at a time, but you care about what happens each time after you draw it out.
Actually, Roshan, it connects even more directly. Because remember when we were replacing open parentheses with A, closed parentheses with B?
It's candidate A and candidate B.
You have to have an A.
You have to have the A
Yeah, yeah.
before you have B, such like that. Except A's and B's. So A's and B's, you've already connected A's and B's to open and closed parentheses, which means the A's and B's connects with parentheses, which connects +1 which connects to this design. So this design actually solves the first 4 problems. It can be used. So after this, we were extremely excited, and we really wanted a formula. So what Roshan did is he took the flowchart, and do you want to get the flowchart?
Yeah, but first so the flowchart, what Isaac said is it looks like half of Pascal's triangle. Because you're taking Pascal's triangle, which starts with 1, 1, 1, and you're just adding numbers. But Pascal's triangle would go along the blue lines, right? The Pascal's triangle would be the full shape, but we're only taking half of that. So, what I decided to do was take Pascal's triangle and take the flowchart and show the differences. Which will, do you want to? Yeah.
Pull down the.
Pull down the projector. And so what the like? Oh wait, we should probably plug it in first.
So what you did was you took Pascal's triangle, you took a flowchart, and you overlaid them, right?
Yeah.
And each of the differences. Because the flowchart numbers were smaller than Pascal's triangle numbers.
Okay.
Wait, David, I have a question. So for your square thing, it's not like this. It's not like the same for every n, right? Well, because
the design gets bigger.
yeah,
It's like
so,
two
yeah, so,
left.
so you have to it's 2 left. So you have to add like 2 to the end, like 2 plus n, right? Like okay, so I did like a 4x4 square here, but it only comes out to like it comes out to a different number. It comes out to like 5. It doesn't come out to 4.
No, cause
Or 14. Oh, you can?
oh, I thought you said you can't touch it.
No, it says stay on or above the diagonal.
No, that would explain a lot.
Okay. Okay, now that works.
Okay, so
Is it turning on?
no,
I think you have to turn it on. I turned it on.
No, it's not in front of it. No, it's not.
Are you sure you're not turning it on?
I'll turn it.
It is plugged in.
Are you turning it on or off?
It's on.
the light is on.
Oh, well, it's yellow. It should be green. I'll text.
We're here. Let's turn it on.
Okay.
Alright, now it's green. That probably means on. So it's probably
So
on
you're
now.
turning it like off.
Okay, this is very important. You might want to pay attention to this.
At least for video time.
We didn't actually get to prove why the formula works, but we did discover quite a few amazing things. Assuming the formula is true.
Well,
Because it is.
last night I figured something out.
Well, Roshan and Isaac made some progress. I don't know what they did. They can show you.
Do I need to do that?
No, now it's turning. Video for now.
Change the input.
Try connecting to the computer. It's the input director.
Technical difficulties.
Computer one.
Getting there.
You're
So
on.
now we're turning
We're
off.
not, we're not using this, we're using analog. Or no, not analog. Not analog. Sorry.
Yes. It's blue, but that's fine.
Wow. Okay. So,
You might want to use a pointer to show something.
well, this is the pointer. The mouse pointer is the pointer. David, point wherever the mouse pointer is. Okay. Okay,
You
never
guys
mind.
read the numbers or?
We can pop
Yeah.
them.
Okay, so this is Pascal's triangle, as you can see. 1, 1, 1, 1, 2, 1. And the formula is each cell is the sum of the cell above it and the cell to the left of it. And it goes on like that.
So this is Pascal's formula.
Yeah, this is Pascal's triangle, really big. And this is the flowchart. So it's the same formula as Pascal's triangle, but all we do is cut off this diagonal because it has to be a staircase pattern, right? So I figured that since they both depend on adding the numbers from the previous cells, that if you take Pascal's triangle and subtract the flowchart, there will be something special with the differences. Turns out that was true. So you take Pascal's triangle, you subtract the flowchart, and here are the differences. So you got one row of zeros, and that just shows that it's shifted down. Okay, then you have, it looks kind of like Pascal's triangle, but it starts at 3 here. So it goes 1, 1, 1, 1, 3, 1, 1, 4, 4, 1, 1, 5, 10, 5, 1, 1, 6, 15, 15, 6, 1. And if you notice, this is pretty much exactly like Pascal's triangle, but you take away the middle number, or one of the middle numbers. There are two of them. So here we have 1, 6, 15, 20, 15, 6, 1. And in the differences, we just have 1, 6, 15, 15, 6, 1. So we realized that taking Pascal's, well, we didn't realize this at the time, now we know it, that taking Pascal's triangle and subtracting a number from a slightly different version of Pascal's triangle will lead to the flowchart, because you're just subtracting in different order, right?
Okay.
Okay, and yeah,
Can we go back to the book?
yeah, flowchart.
Okay, yeah, we're on back to the chart. So really, what we needed a formula was to find these corner numbers, because these were the numbers that related to parentheses and mountain ranges and all that stuff. So if we go back to the differences,
Differences time.
that diagonal of differences is right here. So we can find these differences, and we can coordinate that with the Pascal's triangle. Find those differences and find this. Go back to Pascal's triangle.
Pascal's triangle.
So find the differences and find these. Then we can get the corner numbers of the flowchart. And Isaac was able to find the differences. He found the differences on Pascal's triangle, right? Yeah. You want to go over there?
Or we can do it right here.
Yeah. So,
Well, it's easier to
Zoom
see.
in, zoom in a little bit.
But
so
they-
you can see.
Zoom in, how do you zoom?
Okay.
We need the projector to zoom.
okay. So
Confusing.
what I noticed is that if you take this and just subtract that from it, you get your number. So, and it also works here. 2 minus 1 equals 1.
This is really confusing.
Oh, I'm, okay, that wasn't supposed to happen. There.
Okay, so to get the first one, 2 minus 1 equals 1, which is n choose 1. Here you have 6 minus 4 is 2, which is n choose 2.
It's not interesting.
No, sorry, n equals 2.
Yes, with 2 pairs of parentheses.
Yeah, 2 pairs of parentheses. And then that continues on with this one, with 2, so you take 2n, and you go 2n choose n minus 2n choose n minus 1, or plus 1.
Okay, so basically, remember this diagonal? 1, 4, 15, 56, 2, 10. Now go to the differences.
Did you try to write the formula?
1, 4, 15, 56, 2, 10. That's where the differences show up. Yes. So we knew how to write a formula to find this, can you go back to Pascal's triangle?
Yeah.
We knew how to write a formula to find this column, because these are columns, not diagonals. And we knew how to write a formula to find this column. So what we get is that. What Isaac is writing right now.
And we also have this.
So, well, what we originally got was that, the column minus the other column. And then Roshan did some stuff and simplified it down to that.
No, that's turn on the light and raise it in blue.
Okay.
Put a chance to click like on the other side of the board. print like this. 20 then minus, now gets
Don't turn it off, just cover it up.
Yeah, keep it off. Keep it off. Move the cover. Yeah, very good. Oh, did that look?
Fine, now. So I'm gonna, anyway. So what that says is, this is the formula for the column Pascal's triangle we're looking at. And this is the formula for the column we found had all the differences. So this, if you want to know the number of valid parenthesis groupings you have, this is the formula they want. N pairs of parentheses, 2n choose n minus 2n choose n minus 1. What Roshan simplified this to was two and choose n over n plus 1. Now, this, we're pretty sure, we're 90% sure that this is true. Almost 100%. So, since, what?
We are.
So we are 100% this is true. Now, since this is true, there are a few surprising properties. Sure, you can write them. 2n choose n. If n is the number of pairs of parentheses, so 2n must be the number of spaces, like basically total number of parentheses, counting open and closed. So that's how many spaces you have. Choose n is the number of places, number of ways you can choose the spots for the open parentheses, right? Because there's n open parentheses and then closed parentheses.
Oh.
Okay, now if you, so if you divide that by n plus 1, that gives you all the valids, right?
Why?
Which means everything else must be invalid. Which means that the valids times n must be the invalids.
Wait, what?
So
These,
when you take the total number of cases, this is the total number of cases.
Yeah.
these
When you
are,
divide it by n plus 1, you get the number of vowels.
Yeah.
So we know that when you multiply by n plus 1 you get total. So and one of them is the valid. So n times that is the invalid. That's a bad way of explaining it.
this is the total number of ways, and this is the valids.
So invalids, we can tell is n times that.
Okay.
the other n, all the n plus 1.
Yeah.
There's one n plus 1, there's another n plus n.
Yeah, there's one n plus 1.
And that's kind of how we got from here to here. Both of us. Using the same strategy of
You guys have explanation why the number of invalids is n times the number of valids?
No, but we thought it was pretty cool, so we thought
It is amazing.
So we wanted to show you all.
It is amazing. It is very amazing. Does it match? Could you match them up somehow?
Match what?
Well, I mean, if you want to prove the number of invalids is n times the number of valids,
Like one valid for n.
it's the match, right? Some way of matching them up and seeing if there's some map getting from one to another one. Eventually. We still have, 3 weeks or so.
Right.
So there's more in town.
Yeah.
because if you just look, this will have something inside. It has to start with this and with this. But look, you can start
Oh,
with
yeah, never
this
mind.
and with this. And everything
Yeah,
here
yeah.
is invalid. So there's at least,
So the last one is valid.
except the last one is valid. There.
Oh, you got to find explanation why it's one to n.
What?
Yeah, I believe you'll find explanation why it's one to n. I think you already almost got it.
Okay. So that's formula. You want a formula? That's a formula.
They got the goal because they know they're not that. But it's an awesome beginning and the only way to discovering one of the most important numbers in mathematics. these numbers we discovered, they're gonna be, and they are very, very important. And they have absolutely amazing growth. They grow very fast.
Yeah. If you look
So
at the
people
chart.
tend to know the first 4 or 5, and after that they will spread. But those numbers are super important.
So this
So I suggest you continue to dig and figure out why the ratio of value to invalid is 1 to n. And then we might actually make some progress in discovering a closed formula. That's a closed formula. We can rewrite it in many different ways. But